Okay, so in this video we're going to go through questions 5 through 8 of the enthalpy worksheet. If you're just here for the answers and just want to check them, I have this annotated answer key posted up in the worksheet's answer keys section. I called it Unit 11 enthalpy, so I think it's the way I organized it. It goes like Unit 1, then Unit 10, then Unit 11, and then 2. So just you'll find it near the top. That'll have your answers. But otherwise, stick around for the explanations. So number 5, calculate the amount of heat needed to decompose 25 grams of ammonia, NH3, into its elements. Okay, so we don't actually have to even write out a balanced equation for this. It tells us already the heat needed is 46.19 kilojoules per mole. So that's delta H equals 46.19 kilojoules per mole. Okay. And the reason this is positive is that normally to create ammonia, like to create most of our more complex products, heat is released. So if you want to break it down, heat has to be removed. 25 grams of ammonia. Convert that to moles. Let me just kind of speed this up with my answer key. You guys should know how to do this by now. Molar mass of NH3 is 17.031 grams. Gram cancels gram. And we're left with 1.47 moles of NH3. And now we're just almost doing like a conversion factor. We know it's 46.19 kilojoules per mole. We have this many moles. This times 46.19 kilojoules per mole. Moles cancels moles. We work it out, and we get 67.8. That's 3 sig figs kilojoules. Number 6. Calculate the heat of reaction for the following unbalanced reaction. So that's your hint. First step we need to do is balance this. So we have NH3 again, ammonia, plus oxygen yields NO2 gas plus H2O gas. Okay, and you definitely want to include the state symbols on these because for some examples, like definitely for water, the liquid delta H is different from the gaseous delta H. Okay, calculate heat of reaction. So this is just like problems 1 through 4. We find the total enthalpy change in our products minus the total in our reactants. So let's balance this out. I'm going to start with my N's. So 1N, 1N. H's now. Okay, 2 H's here and 3 here. So when I see 2 and 3, what I want to do is double my 3 and then put a 3 here. So H's are now balanced. But I'm seeing a problem here. We have O2, so this has to be an even number of oxygens. But now I have 3 of these. So I've kind of hit a wall. When in doubt, double it. Turn my 3 into a 6. Turn my 2 into a 4. Let's double check everything now. 4 nitrogens. Well, let me make sure my hydrogens are good. 4 times 3, that's 12 hydrogens. That's 12 hydrogens. We're good. Let's do our nitrogens. 4 here, 4 here. Nitrogen and hydrogen are now balanced. Let's fix our oxygens. 6 oxygens plus another 8, that's 14. So we need a 7. 4 to 7 to 4 to 6. Calculate the heat of reaction for this. So we find the heat of reaction, or I should say the change in enthalpy of formation of these, enthalpy of formation of these, and work out our answer. Okay. NO2, nitrogen dioxide, is, this is a rare plus 33.2 grams per mole times 4 moles. We're going to add that to 6 gaseous waters. So hydrogen oxide as gas is negative 241.8. And times 6 of those. Let's grab my calculator. 4 times 33.2 equals 132.8. Negative 241.8 times 6 equals negative 1450.8. So we're clear on this. That's 132.8. 2. And this is negative 1450.8. If we add these together, this plus negative that is really like subtracting. So 132.8 minus 1450.8, and because we have a 0.8 after each one, I'll give it a 0.0, or a number after the decimal. Negative 1318.0. The unit here is kilojoules. Okay, so my products, total heat of formation is negative 1318.0 kilojoules. Okay, let's now solve for my reactants. Now I can tell right away that's going to be 0, so that'll save us some time. 4 NH3s. Well, ammonia is negative 45.9. So let me do 4 times that. 4 times negative 45.9 equals negative 183.6. Oxygen is 0. 7 times 0 is 0. Leave it out. So my total here is negative 183.6 kilojoules. My heat of formation is the change, or the enthalpy of formation of my products minus my reactants. So make sure you get the order right on this. It's going to be negative 1318.0 kilojoules minus negative 183.6 kilojoules. This minus that. Minus minus means plus. Negative 1318.0, and that 0.0 will play, plus 183.6. We'll report one digit after the decimal point. Negative 1134.4 kilojoules as my heat of reaction. And that matches my answer key. Let's do letter B. 6b. If 10.2 grams of NH3 react according to the equation above, how much heat would be produced? Well, again, we convert grams to moles. So 10.2 grams of NH3 converted to moles. 17.031 grams. Gram cancels gram. We get 0.599 moles of NH3. We're then going to apply that to our energy. So 0.599 moles of NH3. Look at our ratio here. Okay, it was this reaction produces negative 1134.4 kilojoules. Let's copy that down. Negative 1134.4 kilojoules. But that's not per mole. That is per 4 moles. Very important that you note the 4 there. 4 moles of this produces that. So I'm going to say 4 moles of NH3. Moles of NH3, moles of NH3. And we work out the calculations. This times that divided by that gives me negative 170 kilojoules, 3 sig figs. Make sure you put the point there. Okay, number 7. I like this problem a lot. It brings a lot of different concepts in. Negative 7, or number 7. You have a gas stove and you want to make a cup of tea. That means you need to heat 470 milliliters of water from 16 degrees to 100 degrees Celsius. Assuming all the heat goes into the water, how many grams of CH4 will you burn? This is definitely a challenge problem. Well, let's see. First thing we can do is figure out how much heat is going to actually go into it. Because basically, normally in these problems, I tell you a certain number of grams, and you tell me how many joules of heat you get out. Now I'll tell you joules of heat needed. You're going to tell me the grams. So we have a heating curve, and we have 16-degree water. We're bringing it up to 100-degree water, liquid. So we only have to deal with one formula. Q equals mc2 delta T. Q equals mass of the water. Okay, again, never going to be easy in these types of problems. Instead of giving you the mass, it gave you the the volume. Well, because we know the density of water is 1, and the unit for that is grams per milliliter, or grams per centimeters cubed, or kilograms per liter. Best unit for this would be grams per milliliter. So if I have 470 milliliters, I have 470 grams. That's my M. My C for water is 4.18 joules per gram degree Celsius. Gram cancels gram. Delta T, it's going from 16 to 100, so that's 84 degrees Celsius. Degree Celsius cancels degree Celsius. We're left with joules. Work this out, and we get Q equals, with 3 sig figs, 165,000 joules. Now, what you want to do with this is apply this in our chart, but in the chart, all of our values for energy were in kilojoules. So let's convert this to kilojoules, just so it fits nicely into like the data table. 165 kilojoules. Okay, and that's 3 sig figs, 3 sig figs. So we need to generate 165 kilojoules of energy in order to heat up that cup. We're going to do that, according to the problem, by burning CH4, or methane. Well, the burning of methane, let's write the equation out. When you burn methane or combust it, CH4, which is a gas, plus O2, gas, yields CO2, gas, plus H2O, gas. If you put liquid there and do the problem right, I'm talking about here, you'll still get credit. But it does produce gaseous water. Let's balance. 1 carbon, 4 hydrogens, not 4, 2 here, 4 hydrogens, 2 oxygens, so 4 total, 1, 2, 1, 2. Okay, we need to find the heat of reaction of this. So, 2 gaseous waters. For water, gas is negative 241.8 kilojoules per mole times 2 moles. I'm going to add that to the formation of CO2. Carbon dioxide is negative 393.5 kilojoules per mole. So my total enthalpy of formation here is negative 877.1 kilojoules. Here, O2, we know what that is, 0. CH4 is methane. Methane is negative 74.9 kilojoules per mole. It's 1 mole, so negative 74.9 kilojoules. The heat of this reaction is the heat of formation of the products minus the heat of formation of the reactants. So negative 877.1 kilojoules minus negative 74.9 kilojoules. Negative means plus. Negative 877.1 plus 74.9 gives me negative 802.1. I'm going to include the 0.1 because we're adding now. Just make sure I'm good on my answer key. I'm off by like 2 decimals at the end, but close enough. Negative 2.1. The unit here is kilojoules. So this reaction produces this much heat. We are almost ready to solve. In fact, we're ready to do our final step here. So this is the kilojoules per, now we're talking about methane here, per 1 mole of methane CH4. What we're asked for in the problem is how many grams of methane are we going to have to burn in order to produce this much heat. Remember, this was the heat required to heat up that cup of water. So, the way I normally set this up is I start by writing the heat that I need, 165 kilojoules, times, unfortunately I'm going to flip that around. Negative 802.1, just so we don't forget. Negative 802.1. Negative 802.1. 1 mole over negative 802.1 kilojoules, and this is a mole of CH4. So once again, I want to do 165 kilojoules, which is the heat I need. I want to see how many moles I need to generate that heat. So 165 divided by this, units cancel, gives me 0.206 moles. Moles of CH4. We're looking for grams of CH4. One last final step. Molar mass for CH4 is going to be 12.01 plus 4 times 1.00794. And I'll leave the math up to you guys, but this is going to turn into 3.29 grams of CH4. So we basically just calculated if you have a gas burning oven and you need to heat up a pot of tea, that's exactly how many grams of methane you have to burn. I find this really interesting that we can go all the way with this problem. Okay. Number 8. How much energy can be produced if 28.0 grams of N2 is reacted with 25.0 grams of H2? So I gave you the formula down there, production of ammonia. This worksheet, they love ammonia. N2 plus 3H2 yields 2NH3. And really these should be all gases. I don't think it's going to matter. Okay. Well, how much energy can be produced? So first we need to find the enthalpy of reaction, or the heat of formation. Ammonia, 2 moles of it. Each mole of ammonia, top entry on your sheet, is negative 45.9 times 2. Negative 91.8. Natural state of hydrogen is H2. 0. Natural state of nitrogen is N2. 0. Let me just double check to make sure I'm not off on my chemistry. Hydrogen H2 is 0. Nitrogen, is it not given here? It's not given on the front. Let's check the back. There it is. N2 given as 0. So, negative 91.8 minus 0 minus 0. Negative 91.8. And that is kilojoules. That's the heat of this reaction. Ready to move on here. So, in this problem, how much energy can be produced if 28.0 grams of N2 is reacted with 25.0 grams of H2? We're given 2 different masses. We get to do a mica table. Alright, so we need to find our limiting reactant. Let's first rewrite our, let me just move this. Come on. That is the heat of reaction. So, MiCA 1 to 3 to 2. Okay. Let's see how much we initially have. Just to save some time in the video, I understand you guys by now know how to do molar mass conversions. 28 grams of N2 times 1 mole over 28 grams, because that is N2, gives us 1.00 moles of N2. For H2, we are given 25.0 grams times 1 mole over 2.02 grams equals 12.4 moles of H2. Okay. Normally what you do, if it's not obvious, is you see using each of these how much product you get and see what you get less of. That's for your limiting. But when it's obvious like this, we can just identify the LR and the ER. So we need a 1 to 3 ratio. We have a 1 to 12 ratio. It is clear that this is going to run out first. This is going to have a lot left. Okay? If that's not clear, just work out the calculations to see how much of the product you would make with this and with that. If this completely gets used up, minus 1.00, giving us nothing left. Well, if we use 1 mole of this, and it's a 1 to 3 mole ratio, we're going to consume 3.00 moles of this, leaving us with 9.4 moles. And for my product, we're using 1 mole of this. It's a 1 to 2 ratio, so this is going to be, well, sorry, first we have 0. We're going to add 2.00 moles. Let's see how much we get left over is obviously 2.00 moles of this. Mica table is done. Let's check what we need to do now. How much energy produced? Well, okay, so what we need to do is we can honestly just pick any of these 3. I think the best thing to do is pick how much of the product we have. So we end up with 2 moles of product. 2 moles of NH3. Let's set up our equation. 2.00 moles of NH3. Setting up our heat conversion factor right here times negative 91.8 kilojoules per, now let's see how much ammonia we produce. 2, isn't that convenient? 2 moles of NH3. Moles of NH3 cancels moles of NH3. 2 cancels 2. We're left with this number. This is the change in heat. So technically, by the phrasing of the question, how much energy can be produced? 91.8 kilojoules are produced. Okay? 91.8. Letter B. How much of the excess reactant or reagent was left over? We already solved that. Excess. 9.4 moles. If you want to convert that into grams, multiply it by the molar mass of H2, which is 2.01. And for this one, you get 6.06 grams. Okay? That seems high. Ah, yes, that is why. I misread the question. How much of the excess reagent was used, not how much was left over. This much was used. 3 moles of it was used. So you can either answer 3 moles or convert this to grams, and that's where we get our 6.06. So for part B, you would say 3.00 moles were consumed or 6.06 grams were consumed. Letter C, how much excess reagent is left over? Here's my 9.4 moles left over. Converting to grams, we get 19 grams left over. Okay, so that's our worksheet. These last 2 problems were definitely challenges, but I would say if you can get these 2 problems down, you have a really good idea of chemistry, and you've done very well in this class. We've sort of cross-cut lots of concepts in these 2 problems. Okay? If you're taking the quiz on Tuesday or Thursday, you should be ready to go.